In this video, we'll start section 6.2, which will introduce a new function. Specifically, we're going to look at the exponential functions. Now, as I said in our email, there's a lot for all these sections as we get into all these new functions to discuss the basics of the functions, some of their basic pre-calculus facts, their domain, their range, their graph, a little bit with their values and solving equations. And then we've got a lot of the calculus type work, specifically getting into a few questions about limits, understanding the derivatives, a couple of antiderivatives. Anytime we learn a new derivative, we open up new possibilities for chain rule. That leads to new possibilities for U substitutions with antiderivatives. So again, like I said in the email, every time we get into one of these sections, there's a lot, because we really have to get through what is the function itself, and then apply basically all the calculus ideas. But when I say all the calculus ideas, remember, we're not going to go back and do everything from Calc 1. So I've kind of noted there's a few problems. Besides just taking derivatives, I will ask you about finding the equation of a tangent line or finding critical values, two problems that force us to not just find the derivative, but to do something with it. And then similarly, we'll also do a little bit with area under the curve as a way to force us to solve definite integrals. But that's it. We could keep going. We're not doing any more volume. We could certainly set up volume problems with these new functions like we did before. We can go back in Calc 1 and do local max-min problems, absolute max-min, increasing, decreasing, concave up, concave down. So the list could really go on. So even though we are covering a lot, and I am holding you responsible to remember a good chunk of your Calc 1 type of ideas and problems, we're not going to do everything. And again, everything I said will be covered in this video, and will be for all the new functions as well. Okay, so a lot said, let's jump right in. What is an exponential function? An exponential function has the form, I'm already using my function notation, so y equals a to the x, where a is some number greater than 1. We are very familiar with algebraic functions when the variable is the base and the exponent is the number, so x to the 4th, or radicals, the square root of x is x to the 1/2, things of that nature. Those are algebraic. But now we're flipping that, where now it would be the base is the number and the variable is up here in the exponent. That is what we are calling an exponential function. I've got, again, general exponential functions. A is a number to the x power, and as long as a is greater than 1, these will all kind of fall into the same general category as far as a lot of their properties and a lot of those pre-calculus ideas I mentioned are concerned. I'll come back to that in just a moment. So just a couple of quick examples in thinking about values. Again, as long as a is greater than 1. So x to the 4th is not an exponential function, but 4 to the x or 2 to the x. So these are examples over here. 4 to the x, 2 to the x, 1.1 to the x, pi to the x, 10 to the x, right? Any of these are just simply numbers greater than 1, even if it's just barely greater than 1 or a good bit larger than 1, something greater than 1. Now, of course, I'm just leaving plain x's up here, but if there's more to it, 4 to the x minus 1. Well, pre-calculus, that's a minus 1 on the inside. That would be a shift right 1 unit. If I had an extra plus 1 like this here, well, the exponential part is still here. This plus 1 is not in the exponent. That would be an upshift. If I have an extra minus out in front, notice there's a huge difference between this, while this is not an exponential function, and I'll mention what the issue with the negative is in a moment, but that is very different than this. Here, order of operations, 1.1 is being raised to a power, and the negative is just out in front. So all these little things can still happen, and those adjust the graphs, right shift 1, up shift 1, reflection across the x-axis. But for the most part, again, we're focusing on that basic a to the x. Thinking about a few values. Now is a good time to remind you of a few exponential properties. We'll see a few of the others as far as, adding, subtracting exponents, when you're multiplying, dividing, and you have the same base. But I'm thinking more about just some of the fancier exponents. If you were looking at 4 to the 3 over 2 power, how do you evaluate that? Now, certainly, you can use your calculator, and a lot of our calculators, it's the caret button over here. That caret button is what you use for exponents. Fancier exponents, you just need parentheses. Just make sure you enter that for caret parentheses 3 divided by 2, and actually probably use your regular divide sign like that. So, entering them in the calculator, just to be careful with your parentheses and know your sign. But more so than that, we should be able to handle this. Remembering some exponent facts, what are fractional exponents? Well, 4 to the 3/2 power can be treated, they're both the same, either the square root of 4, that whole quantity cubed, or 4 cubed, and then take the square root of that whole thing. With our exponents, we have a fractional exponent. The top of that fraction is a regular exponent, whether it's on the outside or on the inside. And the denominator from that exponent gives me the radical. So this was a 2, hence either of these is the square root. And again, this first one is kind of nice. Either one of these works out pretty nice. If you do it this way, and if you have the choice, if it's going to work out nicely. If I did this as 5 to the 3/2 power, well, the square root of 5 is not a nice number. So whether I did 5 cubed first and then square root, I'm going to get a not nice answer. Pretty much would need my calculator for a decimal approximate, or start off with the square root of 5. Well, we can't do that in our heads. Use the calculator and then cube it. But if it is going to work out nicely like this one does, it won't matter. The square root of 4 is 2, and 2 cubed is 8. Or here, 4 cubed, well, 4 squared is 16, times 1 more 4 is 64. And then the square root still gives me the matching 8. So if we are going to get a nice value out of our fractional exponents, it won't matter which way we do it. So why don't we take advantage and do it the easier way, do the radical first, right? Let's just do one more like that. What if I wanted 8 to the 5/3 power? Well, again, the two choices, 8 to the 5th power, then take the cube root, or the cube root of 8, then raise that to the 5th power. Well, I don't know about you, I do not know 8 to the 5th power off the top of my head, and even if I use my calculator, it would not be obvious to me what the cube root of that number is. So I'll do it the other way. The cube root of 8 is just a clean, simple 2, and the exponent of 5 is still there. And now 2 to the 5th power, I may not know that off the top of my head, but just after a quick multiplication, 2 times 2 is 4, times 1 more 2 is 8, times 1 more 2 is 16, 1 more 2, and 2 to the 5th power is 32. So just working with values, this is a good time to remember. A lot of us, when we think of these exponentials, we're very happy and ready to throw in positive, negative, 2, 3, 4 whole numbers. Actually, it's even good to do a quick reminder on the negatives. What if I had 5 to the negative 2 power? Again, all these things come on the calculator. These are nice enough that the calculator would certainly give you the nice whole number answer. But for us, if we have something like the square root of 3, we'd rather just leave that as the square root of 3, not use the calculator and get that ugly, non-terminating, non-ending decimal. But same thing with the negative exponents. This one's not bad, but some of these can give you some pretty ugly decimals. So it's better to remember the property that negative exponents, we can get rid of them by putting them in the denominator or making that a positive. So this would be 1 over 25. Again, the calculator would just give you 0.04, so that's fine, but just to realize the fractional equivalent to go with it. And like I said, shouldn't need the calculator for that. We should have a good grasp and a good reminder that fractional exponents do make sense. Even if they don't give us such nice clean answers like these couple that I gave you, but that they do make sense. Okay, so now let's come up here and now let's think about the graph. And to get things started, I'm going to pick a really nice one. Let's think about the function y equals 2 to the x. Y equals 2 to the x. Well, I'm going to start off with just making an xy chart. And I'm not even actually going to make the chart. I'm going to do the arithmetic in my head and start plugging in the values. So if I let x be 1, well then y would be 2. If x is 1, I get y is 2 to the first power, which is just 2. Well then if x is 2, then y is 4. 2 squared is 4. If x is 3, I would have to be all the way up here. I'm not even going to try and get my scale, just to try and get it up here. That would be about y equals 8 if I kept going. 5, 6, 7, 8. And hopefully we're starting to get a sense of what's happening if I keep going further to the right. If x is 4, then y is 16. If x is 5, then y is 32. The bigger the x, I'm getting much, much bigger y values over here. But at a quick glance, you might just see these points, and especially I don't have a perfect scale here, but you might look at these and think like, hey, I could just draw a straight line through here. So again, just plotting points, that's not a great way. Let's get a few more values on here. So it's not just 3 points, to see a bigger picture. What is the trend? What is this curve doing? Next, I'll use x is 0. A reminder, as we're talking about different funny exponents, anything to the 0 power is 1. Now, there is a little catch to that. 0 to the 0 power, that's going to be something we're going to have to come back. That's its own special case. But we're already starting with the condition that a is some value greater than 1. So with that condition, yeah, anything to the 0 power is 1. So this just gives me a y-intercept right here. And now hopefully we're seeing that straight line is gone. Now getting that 4th point, there's definitely a bend here. And let's just get a few more. If x is -1, well, 2 to the -1, that's 1/2. 2 to the -2 would be 1/4. And I'll just do one last one. 2 to the -3 would be 1/8. So just as we noticed on this side, x's get bigger, y's get really big. This graph is really shooting up. As we go to the right, this is shooting up very, very quickly. As I go to the left, what happens if I keep putting in bigger and bigger negative values? Well, -4 would give me 1/16. -5 would give me 1/32. Doesn't matter that the x's are negative, I'm still getting positive y's, but those y's are becoming bigger and smaller and smaller fractions. That's what I should say, that these y's, 1/2, 1/4, 1/8, 1/16, that the denominator is getting bigger so that the fractions themselves are getting smaller. So overall, now realize that the domain here, I was only using nice positive, negative, but basically all whole number values. But as we were saying over here, the fractions, the decimals, they all make sense. If I wanted to know what happens when x is 1/2, well, 2 to the 1/2 power is the square root of 2. Your calculator, that's about 1.4. So there would be a point right about here. So I could still keep going in. I could fill in, pick other fractions, decimals in between. We could use our calculators to get the y's. And these are coming together very nicely. That especially when I threw this value in here, that now we can see a nice smooth pattern, the most natural way to connect these points, not to connect them with just a nice straight line, but to connect them with this very nice flowing curve. That is our exponential curve. Now, I did this specifically for 2 to the x, but notice coming back for any a to the x, the same basic patterns happen. That a to the 0 is still going to give me 1, so I still have a y-intercept here of 1. That a to this power, the negative x's are going to give me the fractions. So on this side, I'm going to get closer and closer to the x-axis. We'll talk about that in terms of an asymptote in just a moment. And then on the right side, if a is, again, a value bigger than 1, You use those positive whole number exponents, and you're going to get big in a hurry. Now, little differences. Come back up here. If this was 3 to the x, well, 3 squared would already be 9. So instead of having a point here, it would be up here. If it was 4 to the x, 4 squared would be 16. So again, depending on the a, maybe this goes up a little faster. If this was something like 1.1 to the x, well, 1.1 squared is only 1.21. So this point would only be about right here. So, the a, it still has this same pattern and it still gets bigger, but does it go up super fast? Is it a little more gradual? Either way, that's still the same basic pattern. And this is our generic graph for y equals a to the x. Again, I'll still come back and mention why a has to be greater than 1 in a minute, but that's my basic graph. What do we notice about the domain of this function? Well, again, doesn't matter what exponent you plug in. Positive, negative, whole number, fraction, doesn't matter. Anything works as an exponent here. The domain is all real numbers, negative to positive infinity. Doesn't matter how far left you go, how far right you go, you'll get a point that goes with that x value. What about the range, however? Well, the range, we're certainly going up forever, so my y's will get as big. However far you let the x's go, these y's will keep shooting up forever. But on the left side here, and I'm thinking about the bottom, the lowest y, well, this is what we're saying over here. And same thing that we were saying up here. I'm approaching the x-axis, but I never touch it, and I never fall below it. Even if I had 2 to the negative 100 power, that's still 1 over 2 to the 100 power. It's still a positive value. It never hits the x-axis. It never touches 0, but it approaches 0. So the range, the lowest value, we never hit 0, but we approach it. So 0 with the parenthesis, and we go up forever to infinity. While we're here, let's note that this function is 1-to-1. That if you draw horizontal lines, that there is a unique y that goes with each and every x. So this will have a very nicely defined inverse. We will define that inverse as a logarithm. That will be the beginning of 6.2. And we'll use these properties. This is what I was saying in the 6.1 video. We're going to take so much of what I discussed in that video and we're going to apply it. That the domain of this function will become the range of the log function. The range of this function will become the domain. We'll get this whole flip-flop. Over here, again, we've got a y-intercept, 0, 1. When we use our inverse, that'll become an x-intercept, 1, 0. Over here, this end behavior, we have a horizontal asymptote, y equals 0. That will become a vertical asymptote, x equals 0. So all that flip-flopping of x's become y's, y's become x's, that's the direction we're going here. Now, still have a couple more little pre-calculus things that we want to mention before we get too heavy into the calculus aspect. But one other very quick thing. I keep using that extra condition that a has to be greater than 1. A has to be greater than 1. Why is that? So one more quick note. This is just more for your information. We've got everything established. We've got our basic exponential. But let's just look at a few other cases. Let's look at what happens when a equals 1, when a is between 0 and 1, when a equals 0, and when a is just less than 0. All these are functions, but they just don't fall into this nice, neat category that we were just showing right here. For instance, if a is less than 0, so let's let a, as an example, let's think of negative 1 to the x. That would give you an example of a being less than 0. You lose your continuity, right? Thinking about the continuity of these graphs, this is fully continuous on its domain. There's no breaks or holes. This would have problems with continuity because you plug in x as positive 1 and you get negative 1. Then you plug in x as positive 2 and you get positive 1. Then x is positive 3 and you get negative 1. You keep bouncing from -1 to +1, -1 to +1. And this was like -2 to the x. Well, now I'd have something like, well, +1 for -2 to the 0. That still works. But then I get -2, then +4, then -8. Then, I mean, I'm all over the place. This is bouncing up and down. And not to mention, now the domain is also very messed up. Think about -1 to the 1/2 power. That's the square root of -1. We're not dealing with we're not dealing with imaginary numbers in calculus. We're only working with real numbers. We just say that does not exist. So any of the even roots, the square root, the 4th root, the 8th root, anything like that, you'd have it does not exist with any negative value. So it's a function, but it's quite a goofy function. It's got all these breaks and jumps, so there's a lot of weird things. We're not going to worry about that. If a is 0, well, 0 to any power is 0. This is essentially 0 to the x is essentially 0. 0 to the 0 is trouble, but essentially this is y equals 0. That's just a straight line. Similar up here, 1 to the x. That one is truly just y equals 1. Even when x equals 0, that works. So both of these are just straight lines. And last right here, what if a is some value between 0 and 1? Well, this is just a fancy exponent trick. 1/2 to the x is the same thing as 2 to the minus x. The x can be distributed to the exponents. 1 to the x is still 1. 2 to the x in the denominator can bring that up as 2 to the minus x. So that can be thought of as 2 to the x, but that extra negative, that negative on the inside, remember in pre-calculus, that would just be a flip, a reflection across the y-axis. So again, it's not that these things can't happen. These two just give us cases we're already more familiar with. This just leads to a reflection that we already have here, and this is a real goofy case. So again, they all kind of work. These work better than this one, but that's why we're not worried about these cases, and we're only focusing on a being greater than 1. Okay, few ideas with solving equations, and we're already going to realize we're a little bit limited here, but we'll do what we can. Solve for x. Let's start with a simple one just to get things going here. 5 to the x power equals 25. Well, I'm not even giving you any technique yet. It's just thinking about it, and this is an easy enough one that just thinking 5 to what power gives you 25? Well, let's just realize that 25 is 5 squared, and we'll realize our best situation is this. If I can get an equation to be written this simply, same base to an exponent. Now, these exponents might be different, but they contain variables. If this is true, well, how can two equations be the same if they have the exact same base and nothing else? Well, then the exponents must be the same. So that will allow us to simplify that equation. So here, that's the key. You're already starting with a base of 5 over here. Realize 25 can be written as a base of 5. And when I do that, that directly connects and x equals 2. But now sticking with that, but just making it same idea, but just a tiny bit more complicated. What if I had 3 to the 2x minus 1 power equals 3 to the 5th power? I'm already jumping to give you the same base, but just to realize you're not always getting your answer quite so quickly the way we did in number 1. They have the same base, so in essence, when we get to logs, we can talk about using the log, using the inverse to simplify, to cancel. But other people just apply this property, and that means the left exponent has to equal the right exponent. And now you're just solving a much, much more simple equation. 2x minus 1 equals 5. Add the 1 to both sides, divide by 2, and we get x is 3. Of course, any equation we solve, you could always go back, plug into the original, confirm that the left side equals the right. Of course, that certainly works. Even here, what if there was more to this? What if it wasn't just 3 to the 5th power? What if this was 3 to the 5x plus 4 power? Well, then we already recognize we've got that same base, but now this next line would be a little more complicated, but we'd still just have the left exponent equal to the right exponent, and now we just have to solve this. So a little more to it. I'll bring my x's to the left, subtract 5x, and I'll get a negative 3x. Add the 1 to the right, divide by negative 3. And however you want to write it, negative 5 over 3, negative 5 thirds, 5 over negative 3, right? Of course, the negative doesn't make a difference where you put it. Negative 5 thirds. No reason to change that. Again, we do get a lot of nice whole number answers, but fractional decimal answers happen, so that will be perfectly fine for this one. Okay, so like I said, we're seeing just a little bit. I really hope we recognize this is still a more ideal situation, and these are the situations that would give us nicer answers. Even though this answer is a fraction, it's still not that bad. Realize I don't have to make a harder equation. Just look at number 3, 5 to the x equals 7. There is no nice way for us to solve that by hand. 7 cannot be written as 5 to a power, at least not without doing, again, some calculator, some heavy duty computational work. So again, this we're still going to need more. And what is it that we're going to need? We're going to need logarithms. And if we need logarithms, it's almost a guarantee the calculator is going to be necessary. We'll get some messy answer. But again, trying to get us back on track, remind us of some properties of exponents. And even if we force ourselves to use logs every time, that's not the best way. We want to start with this approach over here. So one more good one. So we couldn't solve number 3, but just one more good one to finish up. Let's look at, let's go 4 to the x squared minus 2 power equals 64. Well, this is pretty similar to number 1. And, you know, we're not always so lucky. 4 is already written to a power. Maybe I should have done one where this wasn't already a base 4. Maybe I should have done one where this is a base 2, and then we can convert this to a base 2. Again, we'll get more practice with this. We'll come back. We'll see some logs, and then once we have the logs, we could kind of come back and do a few more of these. But for this one, just to realize these equations. Now I'm back 4 to this power, 4 to this power. I've got my more simple equation, but just to realize, both of these earlier simpler ones, isolating x, here you could isolate, but when you take the square root, don't forget the plus or minus. Or for other people, you start getting a higher power, they prefer to factor. So I subtract the 2 over, get this in terms of 0. Now I can factor. Each factor equal to 0. And just another way, just for this problem, just to make sure we don't miss the plus or minus, that we don't accidentally just get an answer of positive 2 when we should have an answer of both positive and negative 2. Okay, very good, everybody. So, a lot of pre-calculus work, reminders, just exponents in general, a lot of little things that have come up so far. You know, some of these problems we could keep going. That, you know, why don't I just do it quickly? If this was 4 to the 3x minus 1 equals 32. This could be 4 times 8, but that's still not good enough because that times 8 is still there. And I need it to be 4. That's it. Not extra stuff. It's got to be exactly 4 to a power, 4 to a power. Well, I can't do that so cleanly right here. So let's bring in the 2. Realize, well, 32 can be written as base 2. And then over here, this can happen as well. 2 squared to the 3x minus 1. But now, before you start simplifying and just making this the x equal y, this exponent equal to this exponent, well, first you have to clean up the exponent. So rules for exponents, raising a power to a power is multiplying. So 2 times 3x minus 1. And now we're back to a simpler case. Now I can finally get rid of those base 2's. 6x minus 2 equals 5. Add the 2, divide by 6, and we would get 7 over 6. So like I said, there are other exponential properties. I could have had a 4 times 4 to the 3x minus 1. You're multiplying, add the exponents together. So there's other little good practice that we'll get here. But let's finish this first part of the video thinking a little bit about the beginning of limits. What happens when you take the limit of a to the x as x approaches infinity and as x approaches negative infinity? Thinking about these two limits. Well, the easiest way to start is by looking at the graph. Again, I'm specifically picking on a plain simple a to the x, nothing more to it. But now, what are the other little things that happen from here? Well, just first thing, let's just use that. Look at the graph. X goes to positive infinity. What happens to the y's as you go forever to the right? As x goes to positive infinity, we're going forever to the right, and the graph keeps going up. So as x goes forever to the right, the y's keep going up, meaning a to the infinity power is infinity. But in this second part, what happens as we go forever to the left? As a goes to negative infinity, this flattens out and the y values are approaching 0. That's what we kept talking about with those smaller fractions. Up here, 1/2, 1/4, 1/8, 1/16. Those smaller fractions are approaching 0. That's exactly what this horizontal asymptote is telling me. Go back to Calc 1, we link that information together. You get a horizontal asymptote when one of your limits as x approaches infinity goes to some whole number, some finite value. So that's what we're seeing right here, and that makes this limit equal to 0. This is the idea, but this is where people can goof up. Number one, I've got a here. We're going to get to the number e in just another few minutes. So we'll deal with e a lot more in this class. And maybe you're not so familiar with that, but I wanted to start generically with a, so we're covered in all cases. And in essence, this is bad habit to write this, but it's a good idea to help you remember it. A to the positive infinity goes to infinity, and a to the negative infinity goes to 0. Because to remember, our first technique when we're trying to evaluate limits is to plug in. So if you plug in and end up with these two situations, we have the results here, we got those based off of the graph, and some people just remember them a little bit easier here. Because watch this, everybody. This is all it takes that can throw people off. We've got a few limits to guide us, but now let's solve a few on our own. Let's evaluate problem number 1, the limit as x approaches infinity 4 to the negative 3x power. I plug in infinity. Now this is difficult, everybody. This, in Calc 2 in general, we deal with infinity a lot more than most people have in the past. And for some people that adds a few little tough elements. We like to treat infinity like a number, but we have to realize it's really a concept. But that we can treat it like a number, huge positive number. So 10,000. What happens when you do negative 3 times 10,000? You get negative 30,000. So what happened here? Plugged in a huge positive number, multiplied it by negative 3, it became a huge negative number. So I'm really ending up with 4 to the negative infinity. I'm ending up with this. So this first limit equals 0. And this is what I was saying, everybody. People memorize the wrong thing. That limits, maybe limits with infinity, they weren't as strong with, or they're just rusty. There's a lot of little possibilities, but we're trying to plug in. And again, I don't mind if you do this on the side, but let's have good notation. We don't want to write equals 4 times negative 3 times infinity. That's garbage. Okay, I understand that's what we're thinking of. And all it takes is just writing this off on the side, not putting it next to your actual problem with an equals, and we're fine. Because that's what we're thinking of, and we're ultimately getting 4 to the negative infinity, and that is what's leading me to 0. But if you just look, hey, it's a limit, x goes to positive infinity, people mistakenly think it's infinity. They're not looking at what happens up here in the exponent. They're just purely just seeing this limit and almost just making it a guessing game with these two. So let's just get a couple more with that. Number 2, what about the limit as x approaches minus infinity? And this time, let's go 10 to the x squared power. Again, quick and easy. People see x approaching minus infinity. They jump right here and say the answer is 0. They don't actually think about plugging in. These two limits are only set up if it is a perfect a to the x. But this is not an a to the x. It's a to minus 3 times x. It's a to the x squared. So those little extra things on the function can make changes. So now, huge negative number squared. So again, if you need to, do it. And when I say huge number, as long as you realize where you're going, you could use something like negative 10. You don't have to use negative a million or negative a trillion. Those are really approaching negative infinity. But just using negative 10, negative 100, that'll get you on track. Negative 10 squared is positive 100. 10 to the positive 100. Negative 100 squared is positive 10,000. 10 to the positive 10,000. Better habit, 10 to the negative infinity squared. Huge negative number squared becomes a huge positive number. This is becoming this, so we're not in this situation, we're actually in this situation. This answer is infinity. Okay, let's just do 2 more here. Number 3. Again, few examples. We've got a lot more. Limits are one part, and they're a nice little part. But to be honest with you, everybody, these initial sections, we practice a little bit with the limits. We want to get some practice here. The derivatives and the integrals are a little bit more important for right now. But the very end of this chapter, we finish with all limits. So all these little limit things that we're doing now, we're going to need to have established so we can do the bigger topic with those limit problems at the end. So like I said, definitely want to focus on the derivative integrals and don't ignore the limits. It feels like that's, there's fewer of those in the homework problem, but if you completely ignore them, you're going to be in a little bit of trouble when you get to 6.8. So let's make sure we're getting used to this little practice like I'm saying here. So number 3, let's let the limit as x approaches minus infinity of 5 to the x plus 4, and then I've got a minus 2 at the end here. Plus 4 is up here, part of the exponent, minus 2 just hanging along at the end. In this one, still seems like, okay, what happens? I plug in the negative infinity, and now you see negative infinity plus 4. Huge negative number plus 4 is still a huge negative number. Negative a million plus 4 is essentially still negative a million. So this is basically still 5 to the negative infinity. But don't forget this minus 2 is still here. So this part is using this. This part is going to 0. But what about the minus 2? It's still there. So we're literally getting 0 minus 2, which is minus 2. Remember, technically there's 2 pieces here. You're taking the limit of each piece separately. So the limit of this whole piece does go to 0, but there still is another piece, just to make sure we don't forget about that. One last one. And like I said, we'll go into the next part of this video, and we'll start getting into the derivatives. We've already seen the continuity part, and we're not going to say anything more about that for now. So we'll just get into the derivatives next. So number 4, how about the limit as x approaches infinity of 4 to the 2 over x power? Plugging in infinity. This is such an easy spot to say, hey, 4 to the infinity, the answer is infinity, but you're getting 2 over infinity. So another little reminder, 2 over infinity, 2 over a huge number, 2 over 1,000, 2 over 1,000,000, 2 over 1,000,000,000 is becoming 0. And 4 to the 0 equals 1. You know what, let's even do one more. I'm at the bottom of my page, so let me just squeeze in number 5 right here. Since all these limits initially were all as limits as x approaches positive or negative infinity, and that certainly was what we were trying to challenge, and all these force us the idea of, again, plugging in infinity. It's not an easy thing to do, but we need a little bit of practice. We get that practice here. I'm telling you, it's not going away. When we get to, chapter 11, the sequence and series, infinity is everywhere in those problems. So it's a good time to start understanding how we treat infinity. We try and treat it like a number, but the concept, a huge number squared, we don't just say number squared is itself, it's even bigger, but what's bigger than infinity? It's still just infinity. You know, negative infinity plus 4. Well, negative 1 plus 4 still gives me a positive, but negative 5 plus 4 gives me a negative, but negative infinity is gigantic. So just adding 4, it's still a gigantic negative value. So like I said, little good bits of practice here. So now number 5, what about the limit as x approaches 1 from the left, and let's do 10 to the 1 over x minus 1. So just to get that out of the way, that is a fraction in my exponent, kind of like here. 1 over the quantity x minus 1, all that is the exponent, 10 is the base. Well, even though this is 1 from the left, I try plugging in 1, and I'm sorry, I want this to be 4. So I get 4 over 0. Again, reminder from Calc 1, that's some infinity. We have to figure out which infinity. Well, the top is a positive 4, that's positive, but how do we get to 0? That's where I need the fact that I'm approaching this from the left. So if I plugged in 0.9, which does approach 1 from the left, 0.9 minus 1 would also be positive. So this is going to positive infinity, and 10 to the positive infinity is infinity. But look at how easy it is for this to change. Well, I'm sorry, I'm very, very sorry here, everybody. I'm very sorry. 0.9 minus 1 is negative. Very sorry about that. So this is negative infinity, and 10 to the negative infinity goes to 0. I'm sorry about that, everybody. The answer here is 0. But this is what I meant to say. If we approach 1 from the right, then we'd have 1.1 minus 1. That would give me the positive. This would then go to positive infinity. So a completely different answer. So like I said, all these problems, just because these two limits are ultimately the key, every time we get to these limit problems, whether we're approaching an infinity or we're not, pretty much all the limit problems you'll see in some way forcing us to use this information.